Yeah, hey, this is Arguflow's first podcast. We're doing it right after the release of our third ever product, Arguflow Vault. Go check it out at vault.arguflow.ai. So I guess the history of Arguflow is that we started in January of this year building a decentralized arguing application on top of Nostr. We built that, got it out. It actually still exists if you want to go test it out. It's at app.arguflow.gg. Kind of hard to use. Might want to check out docs.arguflow.gg first before you look at it. But we built that. It seemed like really only people in China wanted to use it, and we couldn't really get a hold of them. And then we were like, okay, what do we build next? So the thing we started to build next was called Coach. And Coach was meant to be like an AI debate coach. It was pretty good, but not well received. When we announced it, a lot of people kind of said it was bad and useless and like we shouldn't have it, which was fair. It wasn't that great. So we thought about how we could improve it. And the short of it is we needed the ChatGPT model to actually cite evidence, which was like a really difficult challenge to solve. A lot of people were doing it through Google search and other things of that nature, but that gets expensive and the search results are really not that high quality most of the time. So we kind of like went to the drawing board and we saw a project called DebateSum. DebateSum was a publication in December of 2020 by Alan Rausch and his co-author Arvind Balaji. I might be butchering that name, but yeah, Alan and Arvind had built this like DebateSum dataset on what's known as the Open Case List Wiki, which is an open source list of case briefs made by debaters around the world. We saw that and we thought it was really cool. They had a demo search engine at debate.cards that was no longer working. And then we found Denz's project. Denz actually built something called debateev.com, which is spelled debatev.com. Debateev.com is a place where you can go and search the DebateSum dataset, basically. It works really well. We thought it was bloody awesome. And we were like, we really want to use this. So we decided to build our own implementation of it called Arguflow Vault. And this podcast is kind of going to be about all the challenges that we faced building Arguflow Vault, and some things that you might want to be aware of if you go to build a similar project ever, or if you want to use our project to build large language model citation and hallucination prevention in your own chatbot. I'm going to pass it to Denzel. He's going to talk about the first PR where things transitioned in our Rust Actrix Web backend from, we use Rust, by the way, where things first transitioned from the AI debate coach to Arguflow Vault.
Yeah, so the very first PR, we were very lazy because we were kind of just like, we were kind of just down because debate coach didn't do very well. So we were kind of just like, okay, we want to do this other project where we have like debate, we have evidence that's kind of like indexed to see how good we could get as far as searching goes. So we did it. We wanted to have to rebuild everything from the ground up, for like authentication, all the login and stuff. So we just put it on top of our current debate coach backend. So the very first thing we ended up doing in this was we just we had to connect to Qdrint. Qdrint is essentially our vector database. We use Qdrint to store things. And that's pretty much the first PR. We just kind of store some payloads information into a Qdrint vector.
And that was number 91?
That was number 86.
86, yeah. So the interesting thing about 86 is that we started off attempting to use Qdrint as the database which holds the vectors and all of the metadata, because we really wanted to be able to do our filtering within Qdrint and not having to kind of use Postgres outside of Qdrint for filtering. It turns out that's absolutely not viable. The short of it is that Qdrint really does not support database migrations or schema migrations. And being so early in our development cycle, we were making a lot of schema migrations. And if we put all of that in Qdrint, I don't think we ever would have gotten to production.
Yeah, if you look at PR91, PR91 really shows off these issues. Because what happened is in PR91, we had upvotes, downvotes in there. We had upvotes, downvotes, topics, sides, and the way that Qdrint stores this is in JSON as like a JSON payload. So it has no schema. So what we have to do is whenever we unwrap it from the database, we have to treat it as if it's an external entity. So it's just kind of very difficult to wrap it. And if you if the content if you miss any part of the content, you can't even look at the data anymore. It's kind of just like doesn't exist, or you just have to do some weird edge cases to kind of like bump it up to make it up to date, which wasn't very viable for our use case.
Yeah, so that was the first thing kind of discovered, and now I'll kind of like let Denz explain the two database architecture.
Yeah, so basically what we did is to combat the fact that Qdren was completely schemaless and had no promises at all, we decided to go with Postgres as our secondary database. So basically the way the two functioned together was that we used Qdren as our main searching mechanism, so we would still have the semantic search, but we would use the Qdren point ID, which I guess is like the indexed or the ID of the index of like the specific embedding within Qdren. And we use that to correlate that with a row in Postgres, which contained all the metadata. And this really helped us because, first of all, filtering was a lot easier because it's just SQL. And we could search. There was a lot more we could do because now that we had a schema, we could build migrations, and we could also have a trusted, there was more trust in our schema, so we didn't have to do all the sums and had to check for all these edge cases because we could actually have option types and other things. But this was also where we encountered our first major library hurdle, which was Diesel. We ended up using Diesel for our ORM, which turned out to be a little bit of a mistake because it was by far the hardest thing to figure out in this project just because of its weird query syntax.
Yeah. Our database schema is actually pretty complex. If you go look at our docs and all the routes that we have, it's pretty bizarre. And the reason why it's so bizarre is because of that two-tiered architecture with Postgres and Qdren. But we also just have a lot of relational data inside the DB that we need to do joins on. And in our case, the big issue was that Diesel made it super hard. Trying to do joins in Diesel is very non-intuitive if you come from a traditional SQL background. And also, Postgres has this amazing feature called JSON AG. If you've used Hasura with GraphQL, then you've used this feature. And it's one of my personal favorites from the database. When we used Diesel, we basically lost access to that functionality, which really kind of forced us to think about our joins and database schema in a way that at least I wasn't used to. I think it's kind of interesting to see where the pivot to the two-tier database architecture happened. And Denzel kind of found it all the way back in pull request number 109.
109, yeah. That's when we started using the two-tiered architecture. The one really weird thing about this, though, is that now that we have metadata in Qdren, now we have metadata in Postgres, but just data in Qdren, it was very weird to kind of correlate these two things together. So we have to so we essentially have to perform our own joins within the database. Within the actual backend itself. So we get the point IDs and then we do a join on that with the actual metadata that we have from Postgres.
Yeah, and this really caused a lot of SQL complexity because when we were first building out the product, we didn't really think about the amount of DB queries that we were making because basically since we were storing the metadata all over the place, we had so many different tables, we were making a ton of different requests, especially since it was so hard to do joins in Diesel. We were making I think for our search card route, we were making 5-6 requests.
10.
A large amount. And that really slowed down our process. It was about 12 seconds per query. And so we really had to sit down, learn Diesel, and also figure out really conceptualize the way our database worked in order to minimize the amount to now I think we're down to 3. So,
yeah, 2 to 3 seconds on most queries.
Yeah.
Sometimes
exactly.
you get down to 1. It's pretty crazy.
Yeah.
But I think there's an interesting nugget of learning there in everyone always says, don't optimize till you have to. And it's kind of hard to swallow as you're developing because you feel every time you merge a pull request, you're adding tech debt. And we just did that and we stomached it and we would be talking in team chat oh boy, this one's bad. But we merged it anyway. And then when it finally came time to do our release and we started doing searches against the full data set, we were holy crap, this takes 6 seconds. It's not viable. We optimized from there. And it worked. We actually were able to optimize at the end. And, part of that, I think, is the beauty of Rust. to some extent. But it was really cool. Like,
Yeah.
people always say you can do that, and in this project, we actually kind of got to prove that we did it.
I'm gonna be honest though. PR 130, I hated this PR so much. It was a filtering PR. so how PR 130 works is we essentially had we wanted to have filters based off some type metadata stuff. So what this means is that because our metadata is in QGent, our metadata is in Postgres and our data is in QGent, we first had to do a filter based off of metadata on the Postgres side, and then we look at QGent. QGent gives the results back, and then we have to sort the results from there. Then we have to join the results we got from QGent back to Postgres.
Yeah. So like, okay, it's like a 3-step process. The user puts in their filters on the client. Those filters get sent in the search request to our server. We then go to Postgres and get a list of all the QGent point IDs that adhere to those filter requirements. We then give those QGent point IDs returned from Postgres to QGent, such that QGent can only return search results which are in the set. Once we get the search results back from QGent, we then do another join with PostgreSQL to include all of the metadata for a given card. It's a highly complex process that comes with a lot of debt. You have 3 round trips for latency, and it's quite the mess.
It was actually my first PR.
Oh wow, it was. I didn't realize that.
Yeah, this was my first PR. And I mean,
wait, no, it wasn't. You added total page count first.
Oh yeah, that was my very first one, just to see if like I knew how to do like
how to do code.
Yeah, and then this was like the first like hard one they gave me. But yeah, so I mean, the time it takes for a search grows linearly the more QGen point IDs we have, because we have to send all of those over the network. To first we have to receive all of those all of the embedding IDs from Postgres, which takes time, and then we have to send it back to QGen, which takes more time. And cutting that down, I think honestly reduced like a ton of time, because we were performing this on each request, because we had private cards and we also had public cards. And so for the search, we wanted to obviously filter out all the private cards. And the only way to do that, since we didn't have the metadata in QGen, was to do this through Postgres. And that's what caused a lot of our time deficit, to be honest.
Yeah, we eventually moved the private public metadata to QGen towards the end to get search query time down, which was like, again, part of that story of like optimizing at the end.
Yeah.
I think this is like a good point, like making a side though, about kind of like the headspace life cycle, or like the psychological battle to like get to this point.
Yeah.
Because so Denzel and I worked on Coach for like 2 months, and we released it. And like I said, it got totally crapped on. Like people actively hated it, which was really sad because we put a bunch of time and effort into it, thought it was cool. And then, we were depressed, and for like about a week we didn't do anything. We were like thinking about completely giving up on the project. But we basically like decided to build Vault in a weekend.
We can put it out in a weekend and then just say, okay, let's see if they like this, and then just walk away.
Yeah. So we made an MVP of Vault in like 3 days. That was basically like semantic search debative with none of the inline syntax highlighting for the cards. You might not know what that is if you're not a competitive debater. But yeah, you can go to Arguflow Vault right now and like see the syntax highlighting if that's confusing. But anyway, point being, we made like a really dumb implementation that was just semantic search over like the same data set that Dens had for debative. And then we DM'd a bunch of coaches on Reddit and like sent some emails and tried to be like, hey, you're in the competitive debate community. Will you use this and tell us how it is? People checked it out, and we received like kind of meh feedback. It turns out that college debaters either don't like me or are mean, because they were still pretty critical. But like their criticisms made a lot more sense to me, and we decided to like push through and do it. And that's when we actually got in touch with Dens.
Yeah. So basically, they made a PR, or they made an issue on my debate of GitHub, and I saw it, and I was like, at first I was like, who are these people? Like, what do they want? And then so I met with them, and it was really interesting because when I towards like the middle of me developing debative, I had this goal of wanting to extend this to a more generalized data set and be able to use this for more like general applications other than debate, and also implement semantic search, because one of the big problems with debative is that since it uses full text search, the query, like the results are really not that great. And also another thing, like which I didn't realize, is that the longer your query string is, the longer it takes for the search operation to happen. So I really wanted to optimize that. And I actually had started working on like using embeddings, but I never really got far. But then Nick contacted me and he told me about Arguflow, and I was like, this is exactly what I was trying to do. So I was like, let me join this team and I want to actually build this product.
Yeah, so, Den's joined up with us, and yeah, he actually started as an intern. He didn't have experience working production code bases, but we worked it out. Like, he was super, like, we actually worked really well together. There was a ton of productivity amongst like all three of us. And yeah, Den's is like now a co-founder, which is also pretty sick.
Yeah.
It's like actually organically growing the team pretty early in our development life cycle, which was really cool.
Yeah, it was awesome.
Yeah, okay. So like I think that the next
big one was the full-text sorting.
Yeah, okay. So now we have semantic search with Qdrim. Believe it or not, in my opinion, semantic search was a little bit easier to figure out than full-text search.
It honestly was.
So there's this really cool thing you can do with Postgres where you can make Postgres a full-text search engine. And I saw this and sent Dens some bizarre documentation, like really bad, on how to do this.
It was like, it was on the Postgres.com website, and like the docs there, like they're very verbose, and you can't really like understand what the hell is happening like that easily. So I decided, okay, let me try to do this, and I literally spent I think 6 hours trying to figure out like what the hell a TS vector was, and it took me such a long time. And also like another big problem was that Diesel didn't support the TS vector type. So I had to figure out how to like get rid of TS vector from all of the queries, which meant that like so in Diesel you don't have, there's like
wait, take a step back. Explain how full text search in Postgres works without Diesel.
So basically all you really need to do with full text search is you create a column just full of these things called TS vectors, and you can create those like on the creation of the column itself, and it just basically creates a tokenized list of all the or it creates a bunch of tokens of the like whatever field you set it to tokenize, I guess. So we set it to be the content field, which is just a parsed or like a cleaned version of the HTML. And when you do the query, you can do a TS query against this TS vector like column, and it'll do the full text search. So it honestly was like not that hard. It's just like the documentation was really bad. And yeah, so since like TS vector was really not that supported by Diesel, we had to do all of the stuff for that manually. So we had to use a raw SQL in order to actually be able to get the first search and also get the like relevance ranking as well.
Yeah, so okay, Dens is not emphasizing how difficult it was to get Diesel to accept the fact we were doing full text search.
Yeah, no.
So like Diesel had no type for it, and they have this unsafe SQL thing where you can write arbitrary SQL, but the documentation for it and the examples are really not great. So and then Diesel also has like a big problem, and people like to talk about how Rust has really readable error messages.
Oh my God.
People really like to emphasize this. When you work with Diesel, you forget that's a thing. Because Diesel's error messages are unintelligible. Like, we could not figure out what the hell was causing Diesel to not like our thing. And we also couldn't just tell Diesel to shut up. Like, unfortunately, we didn't even figure out how to do like unsafe code. So Diesel is safe, our code's actually safe, which is bizarre.
The other thing is that Diesel itself, even though we're like kind of like talking trash about Diesel, honestly, it made like the really simple queries a lot easier to write, because we didn't have to like actually look up any of the SQL or even think about it, because it was just a simple query builder. But like for the really complex queries, that's where like other libraries like SQLX really like come in handy, because you can actually write the raw SQL and it's a lot easier to use. And another problem we had is that like we had no idea if the raw SQL was even like SQL injection safe, because we were scared that like someone could just like in the search query, they could just inject some SQL and then it would execute, because we had like very little documentation on the SQL
macro.
On this SQL macro to see if it would actually like check for that or not. So we actually had to like manually go out and ask them. And actually, I don't think I got a response. I think we just assumed it did.
Yeah, well, we actually found a GitHub issue where somebody
we found a GitHub issue. But yeah, they didn't even respond to me.
And the Diesel creator was like, head bonk, of course it does. And the guy that made the issue was like, well, maybe you should mention that in the docs. And the Diesel creator was like, no.
Yeah.
But yeah, it turns out it is SQL injection safe to do the raw SQL stuff, which is, again, like insane. Like, I don't know. The fact that we avoided writing unsafe code when it came to making our complex SQL queries work is something that I think is really cool.
Yeah.
Yeah. On the bright side, though, this was a very simple PR.
Once we figured it out.
No, 1.36 was very simple because there was no filtering for private cards at this point.
Oh.
Yeah.
Private cards was created in the next major one, which is 138.
Wait, 144.
144.
The numbers
I'm sorry,
are
yeah.
off.
The numbers are kind of off.
Yeah.
Okay, so 144 is the first PR where we actually had the ability to create private cards that were not private via QDream. And I think this is like another turning point in the project. So at this point, we were pretty deep. Like, not compared to where we are now, we weren't deep at all. Maybe like 200
This
commits.
was in like June, I think.
Yeah, which we were at like what, 200 commits overall? If you
couldn't
go to
tell
the
you.
original like branch for the code, you can probably see it. But anyway, I think like around a third, or yeah, a little bit less, maybe a little bit more or less than a third of where we are at now. And we were like, ooh, there's water behind you. And we were like, okay, at this point, we're pretty committed. Let's make this thing actually good and fulfill some use cases for debate that are cool. I think that, Denz, you had bookmarks, right?
Yeah. We had bookmarks.
But did you have collections?
No.
Okay.
It was just a simple save. You could save cards.
Okay, so this is where we started to be like, okay, let's try to make
Yeah.
something more interesting for debate. And there were a few really key features that we wanted. The first was collections. Collections are basically like groups of bookmarks. I don't know. I got the idea from like Pinterest boards. If like a Pinterest board is basically like a group of bookmarks, and we have the same functionality, which is cool. The reason why that's awesome is because if you're a debater and you are trying to prepare all the evidence you need to rebut arbitrary arguments, you kind of need a collection that holds like all of your block cards or your rebuttal cards. And we wanted it for that purpose. It's also cool because you can create sets of cards which you can share with your teammates or even competitors. And that was like the first key thing. Then I think the second key thing was private cards. You know, sometimes you have like a competitive advantage by not sharing your research or your cards. And we thought people should have the ability to have cards which only they had access to.
Yeah, no. Also, 138, I don't actually remember what actual number this is, but this also introduced card collisions.
Oh, wow.
Yeah, so this PR was a really big PR where it introduced both private and card collisions. So the basic premise of a card collision was that, like, actually, Denzel, do you want to explain what the card collision is?
Yeah. Because like, okay, so the weekend project that we had, the weekend project, like the very first time we did it, was if you have two, we ended up noticing that a lot of the things that we were putting into the data set had like a vector similarity of like 100%. So Nick had the idea to kind of say, like, you know what, this isn't very useful if it's 100% similarity. We're just going to say, you know, we're going to ignore you if you are 100% similar. So we just ignored things that were exactly the same. And what this caused was we had a lot less data that was like usable for you to see like how it is similar to everything else. So eventually what we ended up doing was we said, okay, what if we keep everything that is a collision, everything that is similar to each other, and we store that in Postgres. But then there's a question of how we do vector sorts to that, because we don't want to store all of the vectors that are the same in QDream again. It's just going to make search time way too large. And this caused a lot of complexity with that. You want to explain how we kind of do that?
Yeah. So, okay. The thing that's relevant here is maximal marginal relevance. What maximal marginal relevance is like talks about is a very trendy thing right now, which is weird because it's been around for a long time, but I don't know why it's trending. Maximal marginal relevance allows you to avoid returning results that are all of roughly the same similarity. You kind of want to have like some results at 99, some results at 92, some at 85, you know, like you kind of want to have tiers of similarity. That way users who are making search queries can get a diverse set of results. We were aware of that without having ever heard of the term maximal marginal relevance.
Yeah.
It was just intuitive to us. And the reason why it was intuitive to us was not because of the user benefit. We were just thinking practically.
Yeah.
We were like, we cannot store extra vectors for no reason because it's going to damage our vector DB performance.
It's also going to cost more money.
Yep, because you have to generate more embeddings and host more data.
Yeah.
So we went ahead and we were like, okay, we're not going to store the embeddings that are already of a threshold, which I think we set at 96 and 93%, similar to what we already have. It's like the most similar card already in the DB or in the vector DB. And as a result of that, we created the concept of a collision. A collision is when you try to create a new embedding evidence card that is 93, or if it's less than 200 words, or 96% if it's more than 200 words, similar to another card. In that case, Postgres then stores all the metadata for that card. And we make another record, another table called the card collision table, which says that this new card metadata is a collision with some QGent point ID. And that means that when QGent returns the QGent, like the set of QGent point IDs that specify the search results, we use Postgres to pull the exact kind of like we call a root card that matches that QGent point ID, and then also that root card's collisions. And this means that for every tier of similarity, you can see every card that is roughly that similar to what you're searching for, which is really amazing, especially for competitive debaters that want to see like different inline syntax highlights of the same cards.
Yeah. I mean, this was like actually sort of later down the line. In our first implementation of collisions, what we did is that if a card were to collide, we just made it private so that it didn't show up and we didn't have to deal with it. But then we later realized that we were just simply losing information, because if it's private, only the user that creates it can see it. So the public loses out on actually being able to access all of that, especially when the user wants to make it public. So that was something that we had to deal with later, and that also introduced a ton of complexity with our like search queries and stuff like that.
It was actually very funny because like in the very, very initial MVP, like if you ever submitted a code that was a collision, it just says, hey, you can't do that.
Yeah,
it's a collision. We just reject it. And people probably would have been really pissed off about that, honestly.
Yeah, no,
they would definitely would have been. So that's why we had to fix it.
Yeah.
It's really cool. Like I don't know. The fact that we figured that out without ever reading about maximal marginal relevance, to me, is just like badass.
Yeah, I know. And I think the next, the other thing that we did to like differentiate our feature set from DebateEv was the fact that we could update existing cards. So a user, like let's say a user had a card that they created, but then later they wanted to go back and change it. So we didn't want them to be able to change the actual content, because that would mean we would have to regenerate the embedding for it, and that would create a whole lot of cascading effects, especially since we have collisions and stuff like that. So what we decided to do is we would enforce the fact that they couldn't change the content. But since we were using an editor called TinyMCE, which is a what you see is what you get type of editor, you were able to change the syntax highlighting in the browser itself. So we let them do that, but if they change the content, then you would error. And that was 148.
Yeah, that's crazy. 148 is one that we ended up revising too.
Yeah.
Because we were initially using okay, here's another like mini story. So there's a Rust crate called HTML5 Ever, which the Rust version of Beautiful Soup is based on. And this library is bad. So like, this is I think the other really cool thing about this project. People say that languages are tools pretty frequently. And in this project, we really realized that languages are tools. The core server is written in Rust. The parser for when you upload a docx debate brief is written in Node. The verification system, which we haven't talked about yet, but there's like a whole system that verifies that quotations from a given source are actually in that source to ensure data quality, is written in Python. So we have a Node.js, Rust, Python web server, which is probably not that uncommon. But for us being kind of early in our careers, it was really cool to build a service that actually used that diverse of a set of technologies.
Yeah. I think the next big PR is 142.
I think you forgot about deletion, actually. Deletion is pretty complex. Oh, wait. Is that before? Or
oh,
after?
No. That is before. Yeah. The
deletion is actually very complicated
DB
because
transactions.
yeah, DB transactions.
We learned about.
This is very complicated because we have private cards, and we also have we can't just do a cascade delete like we would normally do in like a Postgres database because we still have QGen data. So, and then on top of that, we also have collision detection and collisions, perhaps. So if we ever have a card collision
And bookmarks.
and bookmarks too. So if we have like a if we have a card that is like the root card, like the original the first card that isn't that hasn't been collided with, has no collisions. If we delete this card that is unique, and like it has a link to the actual QGen data, we would have to update something else that is not private, that is not a collision, that is currently a collision with it. So it got very, very complex from that, and trying to manage like just like not having old data and transactions was very, very tough in that.
Yeah, no, like I originally implemented the deleting logic prior to us like completely like expanding the amount of tables we had and the amount of like foreign keys and stuff. So I mean, and for a while we were so busy that we didn't even test the endpoint, and then like I think midway through development, we tried to delete a card because we were testing, and it just broke. And we were like, what's happening? And then we had to go through this entire process to figure out, like, oh, there are foreign keys that are causing this issue. And it's like a whole bunch of control flow stuff now to actually delete a card.
Yeah, I'm pretty sure how we figured it out is we had we setting the database, but we resetting both the Postgres, only the Postgres database, not the QGen database. And you realize when that happens, things very weird happen. So, and then at some point we were like, wait, this isn't happening from us resetting it. This is just a deletion happening, and things are staying in QGen.
Yeah.
So we have to wipe it out of QGen also in the front end. I mean in the Postgres.
Yeah. I think the next big one is 151, where we actually start to upload files.
Yeah, okay, so this is like the next big push.
Yeah.
Basically, between 151, which is June 22nd, and our release this week, we've been working on close to the same like milestone.
Yeah.
What we did is we had an initial upload of all of the docx briefs from open case list, but we didn't get the HTML with the syntax highlighting. We only got the raw text. And we had this goal of re-uploading every single brief from open case list without paying OpenAI a crap ton of money.
Yeah.
And to do that, we had to build a bunch of stuff, which, you know, is what you start seeing at number 151. Because in number 151, we begin to prepare for what we call re-upload. And yeah, like, you know, re-upload starts to get complex.
Re-upload does start to get complex. Yeah, so I think...
So with re-upload, we had to also store the we also wanted to have the docx files be stored in there so they can download them too.
Yeah, so we had to set up like Linode and stuff.
Yeah, we had to have S3
I
set up.
I want to talk about this first. So there's not a lot of guides on Rust Actix Web file upload, believe it or not.
Yeah.
The only guide I found was on using multi-part forms to actually perform the upload. That's really like not great for our use case because we have a bunch of metadata that we want to include when we upload files. And as a result of that, we had to implement upload twice. The first time we implemented it, it was as a, it was using the multi-part form data from the upload, and instead of a base 64 encoded string. And we eventually changed it to a base 64 encoded string, which was in number 157. And that was like a big deal because that was absolutely required to like get us across the finish line.
Yeah, no.
And then we had all the stuff with like S3. So, you know.
Yeah. And then the original parser we were using, or the original converter we were using to convert docx to HTML. I actually don't remember what library it was. Yeah, we were using pandoc at first. But the thing is, like, we really wanted to be able to get underlining, highlighting, font size, because those are really important for like competitive debaters to determine like what's really important in the card. So we actually switched to LibreOffice, and that was a huge switch because one, it actually meant that we actually had like the highlighting and all like the metadata stuff that we wanted, but also it meant that we were making, I think this is the first time we actually used like the command crate in Rust, where we would call out to another process. And so we called out to LibreOffice, got its response back, and that's how we did it from there.
And this was complicated because pandoc, we were allowed to be multi-threaded. So you could convert multiple documents at once. LibreOffice, you can only have one conversion going on at a time. And in our, little semantic search engine, we had to add a mutex, which, you would think is a bit out of scope for something like this.
Yeah.
But yeah, we have a mutex, like a lock on LibreOffice, and that was kind of our first synchronization construct. But I guess like from there, I feel like the next cool thing is we then kind of start to try to do re-upload. So for a couple of weeks, we thought we were like days away, and we were not days away. It took a lot longer than days. But yeah, verification stuff happens in here. Like there's some interesting stuff there.
Yeah.
You want to talk about it for a minute or two?
Yeah, sure. I mean, like verifications, honestly, it's like, it's not, like in concept, it's not really that hard. All we do is we get a web page, so each card has a link, and we add the content to the card. So basically what we do is we make a request to the website, scrape all the words from it, and then do a fuzzy text match to see how many of the words within the content are contained within the actual web page itself. And if we have like a threshold, I think greater than 80 is the score, then we actually are able then we say that it's verified. And we used Python to do this because Python was a lot faster and it was a lot easier to do than Rust.
It's a node server. So like, okay, the verifications
yeah, for verification
are a node microservice that calls out to Python. And talk about Puppeteer cluster.
Oh yeah, so basically, prior to me finding Puppeteer cluster, Puppeteer we had to manage manually. And the issue with doing that manually is that sometimes like the Chrome process would crash. It was really hard to do concurrency because it was really hard to construct multiple browser objects and call those like with different configs. So basically, I found this package called Puppeteer Cluster, and it was really awesome because all you had to do was specify the amount of clients you wanted, and then queue tasks to it, and it would execute it and handle all the concurrency automatically. And verifications are still running. It's probably going to run for another month. These take like a really long time.
Yeah, opening up a web page is very slow.
Yeah, and a lot of the links point to websites that are either deleted or like need auth or behind paywalls. So it's really hard to verify those as well.
Yeah, and I think like that's, that was a big process. Like it does.
Yeah, we had a lot of our own hardware. We actually have a computer in his apartment that's doing the verifications right now. Actually.
Yep, and it's gonna keep going.
It's gonna keep going.
Several more weeks. Yeah. Now I think like the next cool part of this project is, again, you would think basic search engine, not gonna be too bad, and but it turns out uploading how many files was it? 47,000 files?
For what?
Case briefs.
Oh, yeah, 52.
Okay,
like that.
Something like 50,000 files. If you do that on a single machine, it takes, weeks. So at this point, we decided we were going to build a distributed system, which basically means that multiple servers are able to parse documents and upload them to the database concurrently. And yeah, Denzel did most of the work on our distributed logic.
Yeah, so I had 3 computers in his apartment, and so basically there was a few things we had to do. The first thing we had to do was we had 2 options as far as how to upload them. We can either upload it directly to our databases, which is QGen and Postgres, or we can just hit a single server. It would be stupid to hit the single server from 3 different accounts consistently. That's just going to be a DDoS. So we each of our individual uploaders have our own server running that just connect to the databases,
which is Postgres and Redis. So like
Postgres, Redis. Oh yeah, I forgot about Redis.
So like yeah.
So it's Postgres and QGen here.
And Redis
that they connect to, but they also have a Redis cluster that they connect to synchronize, to know what they're uploading at the current time, so that they won't have the same upload. They won't have duplicate uploads.
Yeah, so like we prevent uploading the same file twice using Redis as our cache. It's like key value store.
Yeah.
I remember like Dens was quite shocked at how well Redis scaled. Like
yeah, honestly, like I had never worked with Redis before, and it was handling like so many write operations per second, and that I was really surprised. And it was really small memory footprint too.
Yeah, it was dope. Like Redis was really cool. I'm trying to I think that. I don't know. Well, the next thing that I'm kind of proud of is our parser. So people have made this data set before, this debate some data set before. Like I think there's at least 3 projects we know. There's DebateEv, Logos, and Arguflow Vault. We actually have a blog post up on blog.arguflow.ai where I show all the other things that have kind of worked in the space. There's been a lot of people that have done amazing work. And we have, I think, the most advanced parser. We have like some crazy bizarre logic for making sure that we get accurate cards. We like, I don't know, I'm not even gonna explain it all, but it's really cool. Like if you're interested in parsing open case list briefs in the future, yeah, you should hit us up. We're your guys. And like, I think the funniest thing is in the parser, we wanted to have the ability to parse multiple files at the same time.
Oh yeah.
And to do that, we have a spin lock.
Wait, what?
Yeah, the spin lock in the parser. So
Oh,
like,
yeah, but you forgot to mention the Stack Overflows too.
oh, okay. We skipped over like, again, like this was a month long because we had a bunch of bizarre issues. We had a Stack Overflow. We lost our Qdrum volume.
We had a heap overflow too, didn't we?
Oh yeah, yeah. Well,
we had some memory set happen, right?
we had a kernel panic.
We had a kernel panic.
So basically what happened was that like some of the documents were PDFs, so we would try to convert those to HTML. But the thing is, like sometimes a full HTML of a PDF just wouldn't fit in the heap. And
In
so,
the stack.
No,
or
stack.
in the stack, and then we try to allocate it on the heap using like box. But it turns out when you put something as a parameter into like a constructor, it puts that on the heap, or it puts that on the stack, and it completely blows the stack still. So like there was like literally no way around this. So we really had to move to like Node to actually be able to do all of this conversion and stuff.
This is the reason why we have a different server for this.
Yeah.
Yeah, yeah.
Because initially we had it all on the same, and then the PDFs would blow the stack, and what else? There's one other thing that was a really big issue from it, right? Just very slow.
Yeah.
Yeah.
Terrible.
I mean, I think that like covers like most of the cool stuff that like was done on the engineering side. I think from there, like from 360 onwards, it's mostly just like little bug fixes. And the service that you guys get to go use today at Arguflow.ai is goddamn amazing.
Yeah.
We fixed all the bugs. Like if you find a bug, let us know. Discord, Matrix, Telegram, they're all linked at the bottom of Vault. We're kind of like going to go out and prove that the system we built is flexible. So we're going to go build Semantic Search for Railroad right pretty soon, hopefully next couple of days.
Mm-hmm.
Railroad's like a place where you can upload fiction stories, and we want to add Semantic Search to it. See if we can make that work, make that be cool. After that, we are also planning to do some work on maybe government contracts, provide some Semantic Search for that. We saw like a cool startup doing it. Think we can maybe go compete. But yeah, if you guys are interested in building AI data platform Semantic Search solutions, we highly recommend getting in contact. We think our code can help you a lot. If you want to help contribute, everything's open source. We take open source seriously. Make it like we have issues. The development channel's open to the public if you want to join it. And we think it's really cool. We hope that you guys do too.
Yeah.
Might be back at a later date recording the podcast, but
Yeah.
Yeah.
We have to talk about AutoCAD at some point too later on.
oh yeah, maybe next podcast we'll go over AutoCAD.
Yeah.
Yeah.
I feel like it needs to get tuned a bit better.
Yeah, and we're going to work on it. We're in touch with Alan Roush from the Original Debates and Dataset and trying to reach out to a few other researchers to build a better AutoCAD.
Yep. Yeah. Basically it.
Use the thing, vault.arguflow.ai, get in contact, Discord, Matrix, Telegram, and thank you guys so much.
Mm-hmm.
Yep.